John Lekner is Emeritus Professor of Theoretical Physics at Victoria University of Wellington. After a master's degree at the University of Auckland and a PhD at the University of Chicago, he taught at the Cavendish Laboratory, Cambridge, where he was also fellow and tutor in physics at Emmanuel College. He has worked in statistical physics, electromagnetism, quantum theory, and fluid flow. He is the author of 178 papers and of the books Theory of Reflection, 2nd edition, Springer, 2016, Theory of Electromagnetic Beams, Springer, 2020, Electrostatics of Conducting Cylinders and Spheres, published by AIP in 2021, and Theory of Electromagnetic Pulses, 2nd edition. Now, I'm going to invite John in about 5 minutes, but it has been requested of me to set the scene by speaking to you for 5 or 6 minutes on the subject of cancer. And as all of you will have seen from the abstract, that John has performed some very interesting theoretical work, and I've read his work on electroporation and how this work could assist in the delivery of anti-cancer drugs. But you will also be aware that John is giving his lecture, his talk to us tonight, in honour of 3 of his colleagues, each of whom passed away from cancer. And given that I personally have a long-standing association with the physics community and with Victoria University Physics, and was lectured by John, I think this is entirely appropriate. It happens that I knew these people as well. I knew Paul Callaghan, I knew Pablo Eshegawin, and I had Pablo Eshegawin give a talk to the Royal Society Wellington Branch 2 or 3 years before his untimely passing. And I too, like many of you in this room, was lectured by Dennis Sullivan. He took me and my class for a course in advanced classical mechanics one year, back in the year 1980. So I am going to, I've agreed to give 5 minutes on the subject of cancer, and then I'll call John to give his talk to us. I'm now going to finish. Finally, I want to say that we need excellent research into cancer, its identification, its treatment, and into the ongoing care and support of cancer patients and their family. Now it's my pleasure to welcome John Lekner, my own former professor of theoretical physics, to give us his address. And we are honoured to have John here tonight because of his wonderful half-century of contributions to the life of Victoria University. Thank you, John.
Thank you very much. Good evening. David, where are you? Okay. Thank you for a very moving introduction. When David asked me to give a talk and I chose the topic beauty in physics, which you will hear some of, but David insisted, and I can very well understand why, insisted that I also talk about electroporation and cancer therapy, and that's going to be the first part of the talk. I've got 35 minutes, so I'll cut out some of the what I did mean to say, but that'll be a relief.
We've got time, John.
No, it'll be a relief to the audience. Now, so I had lots of motivation to get interested in cancer, and these are my colleagues and friends. These are my colleagues and friends from Victoria University. They're wonderful guys, fine physicists, and I would say that Pablo especially, but Paul also died in the prime of life. Dennis was 77, but he was working on a book on astrophysics, and so he's 32. I will have to be careful not to say, start talking about any of these guys, because I could be the rest of the talk and I still wouldn't have done them credit, so I'm just going to go on. So cancer, the main thing about cancer, it's our own cells and they are dividing in an uncontrolled fashion. So they grow into tumors. Then if you're very unlucky, the cancer can spread and then metastasize, and you will, that's much harder to treat. So the question is how to deal with it. Just set the scale here. So basically we're on the right hand side at say 10, 20, 30 microns for the cancer cells and for our body cells. A micron is a millionth of a meter, a thousandth of a millimeter. So that's what we're made of, these cells. And electroporation is a means of getting drugs or genes into the cell. And because the cell membrane, which I'll just say a little bit about, controls what goes in and out. And so making effectively holes in the membrane allows these drugs to come in. This is a wonderful thing, the cell membrane. It's a phospholipid bilayer, and it self-assembles. So it's an important thing in life that to have something that in a way is there for our life to make use of. So these this is a molecular picture of it. The reality is somewhat more complicated. It's when you try to simulate. I'm amazed that people are brave enough to do computer simulations of things as complicated as this. In fact, I find biology frighteningly complicated. It's really, really hard compared to physics. Physics is a dream. Now, what is the idea? The idea is that together with drugs, you would inject, or the genes, you would inject tiny little needle-shaped nanos. So nano means 10 minus 9 of a meter. So it's a really, really small, too small to see, and then you put on an electric field. So the electric field would be across the body. Say you had a cancer there, the electric field would be like this. But by having these nanoparticles amplify the field, the ones I've drawn there would amplify it by 100 times. You don't need the very high voltages across the body. This is what it looks like. This is what, see, here is nice, neat physics compared to difficult biology. This is a prolate spheroid. These are contours. The contours are equipotentials. So this is 0 volts, this will be -1, +1. It's analogous to having height contours in a topographical map. So you can imagine this is a conductor, so it's a one potential, so it'd be flat in the topographical map. This would be going up to it and then down, or vice versa. So that's the sort of thing you're seeing. And where the contours are close together, you have a large electric field. So there's an amplification of the electric field. Even better, these things also, these prolate spheroids or anything of that sort of shape, will rotate to align with the field. So you get the maximum amplification of the electric field by the alignment. So that's a useful, another useful part. This is mathematics of prolate spheroids and field amplification. This is maths of the energy and the torque and other things. I'll just leave it. I'm just going. I'm leaving the details. Okay, I'm not. Later on, I will punish you with some equations, but not yet. I was invited to collaborate or write a chapter in a book by these people who work in Paris, but I know Jelena is actually Slovenian. I declined. They very kindly, I said I would help as much as possible. They very kindly acknowledged it. You notice they put... That's corrected now. Now, beauty in physics. This was my choice subject, and strangely enough, it morphed as I talked about, as I thought about it. So my initial idea was to show you a whole lot of nice pictures from my research. Just lovely, lovely pictures of this lovely picture of that. And then I was going to spoil it for you by explaining it. Spoil the beauty, and in fact it's a saying in our family, watch out or Dad will explain it to you. So but my view of beauty changed a bit as I was preparing the talk, and it's more now the breadth of vision and the unity of that it gives you, that physics gives you. So I'm going to try and convey a little bit of that. But first, the romantic view, or the poet's view. This is Keats. I need to warn you that some pronunciations have changed. Awful has almost reversed its meaning. It used to mean awe-inspiring or wonderful. So please take it in that way. So Keats says, do not all charms fly at the mere touch of cold philosophy? Oh, I should say philosophy, it was then natural philosophy, now science. There was an awful rainbow once in heaven. We know her woof, her texture. She is given in the dull catalogue of common things. Philosophy will clip an angel's wings, conquer all mysteries by rule and line, empty the haunted air and known mind, unweave a rainbow, and erewhile made, as it erewhile made, the tender person's lamia melt into a shade. I think this is beautifully put. Philosophy will clip an angel's wings. Well, let's do some clipping. So what I'm going to... First of all, actually, I share this view. I share Keats' view. There's a beautiful rainbow. You don't want to analyze it. You don't want to pull apart, as it were, and tell your girlfriend or whatever that this is such, how it actually works. At the time, when you're looking at the rainbow, enjoy the rainbow. But what is the physicist's view? So the physicist's view, there are billions of rain droplets, and they're refracting and reflecting light. But the thing that strikes the physicist first, it's not actually colours. Why is there an arc? Why is there an arc? So if you've got your back to the sun, the arc will be at 42 degrees. Then why is there a secondary bow and so on? Well, here is the unweaving the rainbow, and this awful thing that we do. This shows rays refracting, coming in, white ray coming in from the top left, refracting at the interface with the droplet, which is light blue, reflecting at the back, the face of the droplet, and refracting again. And when you work out the geometry of that with a refractive index of roughly 4/3, you find that it'll come out as at that 42 degrees. The colours come because the refractive index of water is about 4/3, but it's a little bit bigger for blue and a little bit less for the red, and so they get separated. So that's why That's part of the story. It's actually only a small part of the story. The much bigger part of the story is wave optics, and this is one of the things that we're going to discuss next. So, here's Maxwell. I was going to say he's my hero. He's a person I admire in many ways. I admire how he was as a person. Sorry, you okay? You okay? Bridget?
Yeah, I was just thinking
You can't see properly?
You're on late in life, and I'm like, it's not that old.
That's right. So late in
I
life.
was just doing some math.
Wait, you're doing that. Oh, I see. You're doing the math.
Yeah,
I'm coming to that. This is okay. Let's go to that. Let's go to that. You're thinking you're looking at an older man. You're looking at somebody who's at most 48, probably 46 or 47. This is cancer is attacking him. So here's another victim of cancer. And by the way, I hope I said, David, that we're really glad you're here and not on the wrong side of that. But here's, as a student in Trinity College, Cambridge, with a colour wheel. He was one of the first to, possibly the first to explain how colour vision works. And he spun a wheel with different colours on it. And he died at 48, as I said, at the same age and the same cancer, stomach cancer, as his mother. Maxwell was just an amazing person. One of the things he did as a graduate student was explain the composition of the rings of Saturn. Here's a beautiful modern picture. In those days that it wouldn't have been nearly as clear, but he showed that it couldn't be a solid ring, it would break up, and it couldn't be a fluid ring, it would go into globules. And he showed correctly that in fact it's made up of dust and little pebbles going up to rocks, meters in size. And this is an amazing achievement for a student. This is a graduate student, took on this problem, which I can assure you is difficult. So Mary and I were in the UK a couple of years ago, and at my insistence, and Mary didn't object at all, was to visit sites related to Maxwell. And one of the sites we visited, we visited his birthplace in Edinburgh. We visited where he grew up and stayed with his aunts in Edinburgh, but also his family home, Lekner, in southern Scotland. That was gutted by fire in 1921. It's run by Captain Duncan Ferguson, RN. And so we went there and were met by Duncan, and who's a colourful character, naval officer who served in the Falklands War, commanded a squadron in the Falklands War. He was happy to tell me some of the incidents in that. Because of that fire, about the only thing that remains that's directly related to Maxwell is this tiling that he designed. Now I warn you, here's trouble. This is, and I'm not even going to apologize, this is one of the most wonderful achievements of humanity, is electrodynamics. And Maxwell was the foremost in creating. So we're talking about electric fields and magnetic fields, E and B. The electric fields we knew before Maxwell, it's to do with charges attracting and repelling and so on. Magnetic fields we knew about, it's to do with magnets and currents causing magnetic field and so on. But Maxwell put it all together, and the especially important are the bottom two equations which relate the curl. Now the curl, the del cross E, that's a spatial derivative. It's a combination of spatial derivatives. And so if the bottom left equation tells you that if the electric field is varying in space, the magnetic field also has to be varying at the same point in space in time, and vice versa. The right-hand equation does that. And it's an amazing theory. It is Lorentz covariant. This is before relativity. Relativity came later, let's say 1905. And in fact, one of the reasons relativity was, as it were, forced upon us is that the Maxwell equations were covariant and they were agreeing with experiment. It's in space-time, so that it's a unification of. Before, we used to think of time as just something like Newton's universal time. It's the same everywhere. But now, what the Lorentz transformation showed us that actually looking in a different inertial frame, you're also experiencing there's a different time. And there's a constant c in those equations, which is the speed of light. So Maxwell was able to show that electromagnetic waves travel at what was known to be the speed of light by measurements on light speed. And so he concluded rightly that light is electromagnetic waves propagating. And this was the first real explanation of what light is. But not just that, the speed of light, because of relativity, this comes later really, but it turns out to be a fundamental constant of nature. It's the limiting speed of anything. And let me give you an example. Let me illustrate it. The speed of light in 1 nanosecond, that's a billionth of a second, this is how far it goes, okay? 30 centimeters. In 1.28 seconds, you're getting, that's how long it takes for light to come to you from the moon. In just over 8 minutes, 8.3 minutes, 500 seconds. That's light from the sun was emitted 500 seconds ago. For the nearest star to our solar system, the Alpha Centauri, it's 4 years and 4 months, and so on. By the way, the nearest star is not one star. Alpha Centauri is a double star, 2 stars circling their common center of mass, and actually another star, so it's Alpha Centauri A, B, and C. There's another star circling those. It's more complicated. But if there's life other than on Earth, it's not much use looking much further than that, because it'll take you a long time to communicate with them. For example, the center of our galaxy, the Milky Way, how far is that? How many light years?
50,000?
Pretty good. 26,000 years. So this is, we were still in the Ice Age. I mean, the Earth was in its Ice Age that's 26,000 years ago. And here's one of these things that I consider so wonderful, is the great unification. So you have, here's a electromagnetic spectrum. Yes, it has light there. It has infrared. We're familiar with. We were at the time familiar with infrared because heat radiation. You know, you've got a heater or a fire. You get heat radiation from it. But now, this is all, that whole spectrum is all encompassed in the Maxwell equations. It's an amazing unification and simplification. Mathematics, I won't take you through it, except that this is, in 2003, I was the first one to evaluate both the energy and the momentum of space-time localized pulse. And it turned out that this pulse was traveling at less than the speed of light. And this puzzled me for a while, and I'll talk a bit more about it. So the explanation which I provided later was that, the explanation at the time I realized it had to be because this pulse was in some way either converging from or diverging, converging to or diverging from a focal region, which is a necessary consequence of having localized, space-time localized electromagnetic waves. And this slide here shows that you can actually rigorously show that what's happening is you have a superposition of the light quanta photons. Okay, so here on the cover of the pulse's book is a pulse that's propagating towards you at 5/12 of the speed of light. And I'll show you some pictures associated with that. Here it is coming towards you just before the focal region, and the contours are energy, intensity, and the arrows are momentum. And you can see it's rotating, it's changing shape, but it's a wonderful thing that these electric and magnetic fields are interacting. The whole pulse as a unit remains a pulse. It doesn't dissipate, things don't go off off on their own. It stays together, it's a unit, it's it's one object. Here it is at its focal region most tightly focused, and here it is it's a little bit later. You can see it's changing shape as it goes, and here finally this is what it looks like in the focal region. It's got a helical nature, and this is an energy isosurface, which means this is at half its energy, maximum energy. I need some more time, so I'm going to pass this. The same thing happens for electromagnetic beams. Real electromagnetic beams are not infinite plane waves as you have in the textbook. They are confined laterally. If they're moving that way, they're generally confined laterally. There are consequences, similar sort of consequences to what we had for pulses. This is a linear polarized beam. This is its polarization. It's all lovely and beautiful, but I would spend too much time explaining it. Likewise this, I'm going to pass by. Oh dear, I'm going to pass by because there's less than a quarter of an hour left.
We have time, John.
Okay. Yes, I know, but I haven't even got to the second part of my talk. I'll tell you this, okay, because it's a nice story. So, what we have on the right, the blue sphere there are two conducting spheres. The one on the right is smaller and has a bigger charge. The one on the left has a smaller charge. And these are energy contours, but also on the big sphere, you see a light region on the right. And what's happening is that the big sphere, even though they both have positive charges, the big sphere polarizes, pushes the charges around, and then you have a region of negative charge, the light colored bit there. And what it leads to is that if you put the spheres close enough, the mutual polarization of the spheres, they will attract. And so I proved this, I wrote it up, I submitted it to the Royal Society, and they rejected it. And they rejected it. The referee said, this just can't happen. I appealed. Eventually, 5 referees and an editorial board accepted the paper. So it now has over 200 citations. Final example for electrostatics. This is something that I think is beautiful. This is a cubic lattice. Imagine those cubes repeated through space in all 3 directions. There's a positive charge on each corner. There's a negative charge moving on those surfaces in the middle, and it can move on those surfaces without changing its energy. Okay, so these are energy isosurfaces. And what I find lovely about these is that the change in topology. That first of all, this surface is isolated, but then the second diagram, the one down below, that one here, you just have contact, and then the topology changes, and then these charges can move through the lattice. So you've got to change a topological change. And what it means if this charge, say, was moving out, a charge was moving out from here, another one would be moving in to the other side. Now, part 2. Quantum mechanics is another wonderful field, and this is, first of all, what is it? It's a cartoon of Schrödinger on the left, and the Schrödinger equation down below. It's a cartoon by Bob Brockie, and it is an equation. We have to go back a little bit and what the physical world looked like around 1900 had some major puzzles in it. There were spectra that were unexplained, atomic spectra unexplained. There was black body radiation unexplained. There were other things unexplained, and something needed to shift. And what Planck made a start, Einstein in 1905 with his photoelectrics made it a major step forward, and the quantum theory, Bohr in 1913 developed the Bohr theory of the atom. All of them using the Planck constant, and so there was a revolution in physics, and what it did was finally we could understand matter, we could understand atoms. I'll tell you a little bit about that. I think it's better if I don't go into detail, but I said Bob Brockie's cartoon, so how come Bob Brockie would have, who in his book on the evolving story of life, from Darwin to DNA, would have a cartoon of Schrödinger? The answer is that Schrödinger actually had ideas about life as well, and important ideas. He wrote a book in 1944, and he recognized that what was needed to convey genetic information was something that was essentially digital. He called it an aperiodic solid. We know it as DNA now, but he saw the necessity for that. And so that's why he features in Brockie's book. By the way, Brockie was a cartoonist, biologist, raconteur. I recommend the book. So what comes out of Schrodinger's equation is that the prime thing is energy levels. So classical system, this is a harmonic oscillator. Classical system, so you can have a pendulum or a mass on a spring, and you can oscillate it with a small amplitude or a large amplitude. Quantum mechanically, there are only certain possible energy eigenstates, and they're shown here for the harmonic oscillator. This is going to take me too far to you see what's on the bottom here? Okay, I'll say the main thing is, so how far have we got? I said we could, and potentially we're understanding the world we live in, which is a quantum world. We understand it, potentially. But from my point of view, I love exact analytic solutions. What we've got is hydrogen. We haven't even solved the helium atom. Part of the mathematics is down at the bottom. And so that's one of the things I'm working on. I'll go back to Schrödinger. So Schrödinger was puzzled by these energy eigenstates because he thought, how come here's a classical motion, harmonic, something oscillating. How come quantum world is so different? Surely there must be a correspondence somehow between the classical and the quantum world. And he constructed, out of all those, I showed you a whole lot of energy eigenstates. Out of all those eigenstates, he constructed what's now called a coherent state in optics. We use it. And what you see there is the wave function, which is constructed out of an infinite number of those excited, harmonic oscillator states. The red curve is the real part, the green is the imaginary, blue is the envelope. And there are two remarkable things about this, at least. One is that the black region is classically forbidden, so that the pendulum only moves between certain angles and depending on how much swing you give it, the energy you give it in the first place. In the quantum mechanical world, that doesn't work. You can have negative kinetic energy in the black region. You could see there's not even a discontinuity, it just quite happily goes into that negative energy region. The other thing is that you're watching perpetual motion. Unless there is enough energy available to make transitions between these states, provided the thermal energy is less than that, this will just go on. It will go on. I mean, that's quite, in other words, the quantum world is quite different from the classical world, what we live as classical, the human-sized world. What we are used to is friction. What we are used to is certainly not penetration into negative kinetic energy we can't think of. Kinetic energy is 1/2 mv squared or p squared over 2m. That can't go negative for us. Well, it does. And this is another example which I better not talk about. Now, forgive me, I'm going to just, this is something, so I mentioned that I very much admire Maxwell, and I also very much admire a lady called Jane Austen and what she did and what she wrote. And this is just a little idiosyncratic thing that I ask your forgiveness for sharing, because it's sort of peripheral, but it means something to me. And so here's Emmanuel College, and I'll go back to that slide in a moment. I was a fellow of Emmanuel College from 1968 to 1973, and the fellows played bowls in the fellows' garden. It wasn't the usual dull bowling game where you have a set field, as it were. It was put the jack anywhere in the fellow's garden, including under the oriental plane tree, which I admired. And I took a liking to Blackall bowling balls, and that this is bowls, and I always played with those. And so going back to here, this is Jane Austen writing first of all to her sister, Cassandra. Our indifference will soon be mutual unless his regard, which appeared to spring from knowing nothing of me at first, is best supported by never seeing me. In other words, please notice me. I wish he would notice me. And I'm quoting it here because as I was preparing this talk, it occurred to me, how is it that we have this sense of beauty, a sense of, and furthermore, how is it that it's so, it's linked to our emotions, we feel it, and I think it may be that it's to do with evolution. The most important thing we do is find a mate and have children, and so there was the beauty idea was initially, I would say, health and fitness in a potential partner, but then it broadened as we've got a brain, we're the beneficiaries of 3.5 billion years of evolution, and we've got an amazing brain and this brain went off and saw other things that looked beautiful, not just men and women, and so there was a kind of a diffusion or a generalization of something which I think may have come from evolutionary pressures. But thinking about this, I thought, well, yes, okay, so I certainly find women beautiful, but is it possible that men can find men attractive? So, or blokes, So, but here, look at the second quote. This is she's writing to her brother now, Francis, or Frank, she called him. I wonder whether you happened to see Mr. Blackall's marriage in the papers. He was a piece of perfection, noisy perfection himself, which I always recollect with regard. So it is possible, and then here's documentary evidence from Jane Austen herself that she did think some man was attractive. Peace, by the way, is misspelled there, but that's the way she had it. So I'm leaving it that way. And so I've told you about the bowls, and so I've sort of felt, because I admire her so much, her writing so much, I felt that this was in some small way I had contact with her. As for Blackall, well, he was adult. Missed out on being married to Jane Austen, but hey. I'm going to finish with a poem. Poets have a way with words, and so although William Blake was a romantic and a mystic, and he certainly was not endorsing science in this poem, he was quite not at all. It fits my view of science, the vision that science gives you, and I tried to stress also the unity that it gives you. It's a kind of zooming, you can zoom in, and so particularly the first line, to see a world in a grain of sand. For me, that's exactly how it is. I see a grain of sand, but I also can imagine, I can zoom in and see the microcrystals, and I can think about the atoms in the microcrystals, I can think about the optics, this is how I see it. So I'm going to finish with this. To see a world in a grain of sand, and a heaven in a wild flower, hold infinity in the palm of your hand, and eternity in an hour. Thank you.
Well, thank you, John. And now I feel we can take some questions. I think we do have time. I've got a microphone here. Please put up your hand if you have a question.
Actually, yeah, can I ask for questions? So I spoke a little bit about cancer, and we've got some people who know about cancer here. Perhaps they would like to correct anything that I said that wasn't right. Do you have anything?
No, I'm good.
It was okay. Yeah. Bridget?
You're good, John.
No.
Yes, we have a question here.
I know nothing about theoretical physics, but because we were talking about cancer, and straight away I was thinking about MRI, which I guess is something to do with electromagnetics application.
Yes.
And with all the others, I was just wondering, like with all the others mentioned here, electrostatics and electrodynamics, fluid flow and quantum mechanics. Is there some sort of a real life application actually with all these theories to help us in medical field other than the MRI?
Thank you. I think the answer is yes, science does. We have an amazing medical science ability now. In Maxwell's time, they could just give him heroin, and that was or cocaine. It was that all they could do was try to alleviate the pain. Now we have real understanding. That real understanding is based on real understanding of physical phenomena like magnetic resonance, and but also optical phenomena, X-rays. All those things depend on an understanding. You also mentioned fluid mechanics. Apologies, I left out fluid mechanics, the fluid flow. I love it, but there was just too much to do. So I didn't talk about fluid flow at all. Thank you.
Hands up. Come on. Must be people with questions.
Just going back to your example of two balls with equal charge, or with both with positive charge, for example, attracting.
Yes.
Did you manage to show that in practice?
There are more than 200 papers on it, and not one of them said I'm wrong, and I think the rest of them, I haven't followed them all, but I think what's happening is people are finding various applications. So there are various, for example, colloidal suspensions, where you have some surface charge on these things moving around. And so this business of like charges possibly attracting, not point charges. If you have two electrons, they're going to repel, right? They're point charges, but as soon as you have some size associated with it, then you can polarize, redistribute charge on those. So I think there are lots of applications, possibly 200 applications, I don't know. I really haven't read those papers, sorry.
Thank you, Professor Lekner. That was wonderful. If I may speak as an engineer who at one stage was associated with a lot of people who use Maxwell's equations in everyday life, Steve Inge was one of them, and you possibly knew him. There's rather a wonderful joke that is told, and it goes to about 30 years after Maxwell died, to the German physicist Hertz, that's right. Heinrich Hertz was busy experimenting to see if he could transmit what we would now think of radio waves from a transmitter to a receiver. And he did. in his first experiment, I think he managed a range of about 3 meters. And there were people who saw this and spoke to him, and they said to him, here Hertz, this is all very interesting, but can there possibly be any use for this this phenomenon that you have discovered? And Herr Hertz said, no, there is no use whatsoever. It all just goes to show that Maestro Maxwell was right.
Well, thank you very much. I don't want to add to it. Thank you.
Thank you.
For the story.
We have, Bruce, we have a couple more, and then we'll have to go and make our presentation.
Thank you very much, John, for your excellent sharing of the beauty of physics. I'd like to take it back to the original water droplet and the reflection and the refraction of light, and ask what's happening at the quantum level causing the refraction and the reflection.
Thank you very much. So what's happening in the droplet is you have a lot of water molecules, and they have electrons on them, and the light wave comes in, and the electric field mainly rearranges the positions of the electrons very quickly. They then have a dipole. So inside that the water droplet, what you actually have is a whole lot of dipoles excited by the light wave itself, and they, together with the incoming light wave, is what makes up the refractive index, which is roughly 4/3. So the light doesn't travel at c, but at speed of light, but sorry, at the vacuum speed, but at 3/4 of it, and so on. So that's what's happening on the atomic microscopic level. But is that the sort of thing you wanted, or not?
I was just wondering, like at the reflection level, what's happening, turning the light around? Why is it reflecting?
Thank you.
Yeah.
What's happening at the reflection level is, so you've got, in classical optics, we just say the refractive index changes and so it reflects. But in the microscopic level, what's happening is you've got some polarized material here and none there. And so the electromagnetic wave that's propagating is sensing a change, and this change of any kind for the electromagnetic wave causes some reflection. So that is reflection. Actually, I've been showing off and showing the covers of my books. The one I didn't show was Theory of Reflection, which is published by Springer.
One or two more questions, and then we'll get to the presentation. For
those of us who are not physicists, you had a slide with all the wavy things on it. Well, you called them the eigenlevels. Can you explain what are those the levels of?
Okay, so what we have is something oscillating. It could be a pendulum or a mass tied to a spring, and that's the classical motion. The quantum view of this is if you actually solve Schrodinger's equation for something that's microscopic and roughly a harmonic oscillator. Actually, it turns out that almost everything is roughly harmonic, because systems tend to sit near a potential minimum, and this is, roughly speaking, a parabolic like this. And then what you find is that only certain possible energy levels exist. There's in between these. There's nothing that the wave cannot doesn't properly interfere with itself, except in those. Okay, so I think you could look at it as wave interference, if you like. Although it's not as simple as wave interference because its potential and kinetic energy is changing as you go along left to right. Thank you.
Another question? Anyone else want to make an observation, get something off their chest? Yes, hi.
I'd just like to ask you, given you're involved in lots of different areas here, how do you decide where you want to explore? And,
Yes.
and also,
Thank you.
what are you exploring now?
Okay, well, actually, what I'm exploring now, one of the things I'm exploring now is at the bottom here, the helium atom. I've just submitted a paper on to do with the kinetic energy operator there. I think I had something. Oh yes, so there's relativistic quantum theory. I have something going in that, and something about to be published. I love fluid mechanics, and I've been neglecting statistical physics, which was my first love in physics. I think, and of course electrodynamics is a joy. So what I've got is 20, possibly 30 unsolved problems, and if I have an idea or one or the other, I try to work on that. So basically I'm trying to find solutions that satisfy me, not computer stuff, but exact analytic solutions. And I get stuck. I usually work for a month or so or two on a problem, and if I'm just hopelessly stuck, then I put it aside and do something else. But in addition to that, Jamie, I'm part of a worldwide community of scientists, so I have friends all over the place, colleagues, who will send me a question or something like that. So, yeah, and former students as well. Thank you. Now, I think David is going to embarrass me again.
You'll be embarrassed, don't you worry. Plenty of embarrassment. John, I might even need my guru here. Guru, please. It's great to have a guru on hand when you need a guru.
Go back to that one.
Yes, that's right, yeah, please. We'll go to the next slide. Look, is that fully visible? Look, John, when you were talking about giving a lecture on beauty in physics, well, I think that everyone in the room here could understand at some level the concept of beauty in any form of science. And what I did actually when I was thinking about it, I dug around into my own honours notes from the early 1980s, from 42 or 43 years ago. And so you gave an honours course in advanced theoretical physics, and I think in my year, Colin Cook gave a series of lectures on the Feynman path integral approach to quantum mechanics. So I dug around, and I was looking at those notes a couple of days ago, and here was a lecture that you gave. You may not believe it, I can remember this particular lecture. Now, these are the notes I took. These are John's ideas, and the physics is not mine. I can claim no credit for any of it. All I did was copy down John's notes from the blackboard. But I mean, it seemed to me when I was looking back in retrospect that there may be, I don't know how you would see it, but more than one dimension to beauty in any kind of science, more than one dimension to beauty in physics. And it seems to me that one dimension is the science itself, some manifestation of nature, an idea or a concept, and that is beautiful in itself. But then it struck me when I was looking back at this lecture from 43 years ago, my handwriting, taking off your notes off the blackboard. There's the nature itself. In this case, it's helium atom, helium-4 at or near absolute zero. You've got these atoms of helium. The other part, the flip side of the beauty of it, seems to me to lie in some kind of mathematical representation. The beauty is inherent in the concept and the nature in its own right, but there is also inherent beauty in the framing of this idea or an aspect of nature in mathematical terms, as you did, and I can remember you writing this on the blackboard, believe it or not, and then subsequently the development of the idea in mathematical terms in such a way that you can now predict And I'm not talking about prediction into the future. I'm talking about prediction in the sense of modeling or explaining some aspect of nature. So that's what it seems to me, what you're getting at. It's the nature itself. It is also the mathematical framing and the representation. That's also beautiful. You also gave a series of lectures and a course in geophysics, which some of us took. I mean, there was the classical, the advanced theoretical physics, in which you lectured. There was a course in nuclear physics lectured by Peter Johnson. There was a course in condensed matter physics, and Joe Troudel, I think, lectured on it, and Andy Edgar, who's sitting right there in front of us, told us everything we know about Brouin zones. But you could also substitute courses from the geophysics group, and there was a course in terrestrial geophysics that some of us took, I took it, and there was a course in atmospheric and ocean physics. Tim Shirtcliffe did the course in oceanic current dynamics and so forth, but you also lectured us on atmospheric optics. And again, I think we see the same idea. There is something in nature that is inherently beautiful, but also the framing of this aspect of nature in mathematical terms, and then the subsequent development in such a way that we see a prediction or an explanation of nature. So I don't know whether you want to react to that or whether you think I've actually caught it. But beautiful, beautiful physics and beautiful, beautiful mathematical representation of the physics. Now, you actually did give a lecture on the formation of rainbows, and I can remember that lecture from 43 years ago. Wow. All right? I can remember you giving that lecture. And so, again, just to repeat what you said, the person is standing to the left, and the sun is behind the person, right? And then you've got sunlight incident on this droplet, but of course the cloud contains billions of trillions of droplets, and then you have this complex series of reflections at the surface, refractions inside the droplet, transmission through, and light being blasted back at your eye, and what you see, of course, is a rainbow, all right? But what I want to end up with tonight is something that you said to all of us, and it's remained with me all these years. What you said was that each and every one of us has our own personal rainbow, okay? And that's remained with me all these years. Now it's our pleasure, not only my pleasure, but to make this award in our appreciation of a very warm half-century of contributions, not only to theoretical physics, but to the life of Victoria University. So last year, I proposed that the Council of the Royal Society of New Zealand, Wellington Branch, awards from now on a special award for lifetime achievement in science, and that John Lekner should be the first recipient of the inaugural delivery of this award. And our council approved unanimously. Why? Because half of them have taken lectures. So, there is and I want somebody to take photographs, please. There is our award, our certificate, a framed certificate, and it says Royal Society New Zealand Wellington Branch Lifetime Achievement Award for 2026, presented to Emeritus Professor John Lekner in recognition of your distinguished career and outstanding contributions to physics. So John, it's my pleasure to make this award. Thank you. Can we go to the photograph? Thank you. And listen, thanks to all of you for coming here tonight. Safe travels, and well done, John. Thank you. Cheers. Cheers. All right. Well, thank you very much.